Hi, my name is Paul Dirks. I am the principal and senior engineer for my company, Laminar Energy Services, Inc. The purpose of this video is strictly marketing. I would like to demonstrate the skills that I have in being able to marry a modern HMI, which is human machine interface graphic that you see in front of you, that is currently operating, to an older PLC system, and I'll get into details regarding this process and the PLC system. And when I say older, I mean the 1980 vintage, prior to when TV screens and monitors were being used to observe automated control of a specific process. So there's information on YouTube there for seeing more about my company. You can go to www.laminarenergy.com to see all the different services that our company can provide. So let's move on with this video and get into more detail what this marketing video is all about. Well, I'm back. So this next section I want to talk about is the process itself before going into details of the demonstration. It helps to understand what this is and to know why it works this way. This is a baghouse filtration system on a biomass power generation unit. The boiler burns wood fuel for heat to convert that heat in a boiler to make steam. That steam goes to a steam turbine, which then powers a generator to make electricity. A consequence of burning the wood products in the boiler is particulate matter from the ash and the wood products just firing away. The particulate matter is not allowed to go up the stack and into the atmosphere and has to be filtered out, and that's what this system is about. So I'll move the cursor on the graphic and you'll see over here, this is the exit flue gas from the boiler entering this filtration system in the yellow pipe on the graphic. There are 12 individual chambers labeled compartment A through K, actually L, sorry. And each chamber participates in cleaning the flue gas. The inlet pipe is the yellow, and I'll just follow this into compartment B up here. This is the B inlet valve, goes into the chamber, and you can see a lot of YouTube videos on the internals of a baghouse, but it's just fabric bags that hang, and they catch the particulate matter on the outside of the bag and allows the flue gas to pass through the bag and then through the outlet pipe, which is in blue, through the outlet valve, and then on towards the stack. Now, it's very important to maintain the freedom of flow through all of these pipes. So this system and process on this biomass unit has a cleaning system. And the way that works is each compartment individually can be cleaned in a sequence from A through L, one at a time. And when the cleaning of a specific compartment is initialized, the outlet valve is closed and the gas recirc fan over here, recirc air blower, pushes air back through and collapses the bag, and the ash on the outside of the bag falls off and drops out And so what's not shown on this graphic is the conveyor system that then transports the ash off-site. So logic is needed to sequence each one of these compartments, open and close the valves, and provide indication to the operators of what's going on. So that's the basic principle of how this works. You'll see this in more detail in a later section of this video as I place this process into automatic to demonstrate what's going on. As I stated earlier in the marketing video, I built this HMI graphic and fully functional simulator integrated with a Modicon PLC, an older version, to demonstrate my skill at being able to integrate these two functions and create a very highly intuitive, user-friendly graphic that makes operating this process a lot more reliable, safer, and easier for operations. And that's the purpose of this graphic that you see in front of you. Now I'll give some background on where I began with this project. This is my bench test Modicon Quantum PLC system that is similar to the client that I was doing this project for. I purchased this from eBay, and the client would need to add the Ethernet module you'll see on the right to because the graphic is server-based and the graphic is has a client that produces this that reads this graphic from the server and populates the different data fields. The original site configuration is this panel board. This is typical of the 1980 vintage because TV screens were not widely used, and it was easier to put the PLC in behind this cabinet and use these cardboard ways to model the process. And you can see the similarities to what you've seen earlier. Here's the flue gas inlet. There's the inlet valve to compartment B, representation of the baghouse, and then the outlet, and then back to flue gas outlet, common pipe to the stack. And notice here that the information available to the operator is simply indicating lights, switches, like here, a selector switch. Here's their postage stamp style annunciator window that I've also included in the graphic to give alarm annunciation. I'll scan down here to show you more of the same panel. I couldn't get all 12 chambers on my camera shots because of the size of the control room. Here's indicating lights that show the status of various things that are information only. And these are being driven by digital outputs on the rack, PLC rack, and the selector switches and push buttons are being used as digital inputs to the PLC rack. Whereas in my full simulation, I built additional ladder logic to simulate these field devices. This shot here is the representation, an example of the ladder logic that is inside the Modicon Quantum PLC. And the point of showing this is it's very difficult to go through all these pages of ladder logic and keep in memory, your own personal memory, what these contacts and coils are doing to discern what the original manufacturer had in mind in their design. And as I say, this was an existing system when I toured the plant, and I obtained a copy of their logic, loaded it into my bench test Modicon PLC, and started breaking down this ladder logic. And one of the skills that I have is reverse engineering, that I can go through each one of these pages of the ladder logic, and I redraw it up into Boolean format, which is simply AND gates, OR gates, and whatnot. And what this does for the way I break down and reverse engineer client systems is allows me to understand on a whole page the intention of groups of ladders that may take anywhere from 10 to 30 pages of ladder logic to determine what this functional logic is doing. So to build the graphic that I did build, I first had to learn what was inside the PLC that was designed by somebody else and break it down into this Boolean logic format. And once I was able to understand the various sections through this type of drawing, I could start construction. And the graphic that I built in here, as you can see, I'm using Rockwell's application program Factory Talk View, which I really like because of its capabilities. So next we'll start talking about actually how this system works now that I've covered the process by which I did my development work. Before we do some of the fun stuff, which is placing this fully functional simulator on a baghouse filtration system into action, I want to just briefly summarize what I can do as an engineer, as a contractor for potential clients. This simulation is simply an example of a broader area of work that I can perform. And the example I'm discussing is I took a Modicon Quantum PLC. In fact, I had absolutely no experience with these until I built this simulator. Self-taught myself the hardware configuration. In addition, how to use ProWorks 32. I chose ProWorks 32 because it's on an old Windows XP laptop instead of using Unity Pro. But I taught myself how to read, configure, and make changes and additions to the Modicon. And then the cool part about this is, since I really enjoy Rockwell's, let me back up a minute. I reverse engineered this logic and created it in Boolean form so I can get an understanding of the intention of what the existing contractor who installed this logic had it as an intention. And that's a skill set I've done over the last 40 years of being in this industry, which is primarily my experiences in the power industry. But this process of taking any PLC and marrying it with any graphics package is something that can be applied not only to any portion of a power generation unit, but it also can be applied to manufacturing. There's many older styles of processes or processes that a client would like to automate. And I am skilled at, in this example, reverse engineering of an existing control system. But in addition, I have designed from scratch many control systems and done full automation of a specific process. The process doesn't have to be just digital. As an example here, I'm very adept at regulatory control, analog logic, and designing very sophisticated and advanced control systems that and have many examples of stabilizing and automating various clients. Here again, please go to www.laminarenergy to see the full extent of my capabilities. But continuing back to this, once I understand the Boolean logic, the intention of what the original designer was doing, I could then create the graphic to follow along and interact with this logic in the PLC. And by the way, the PLCs that my favorite is Rockwell's Allen Bradley control logics, but I have done extensive work in many Rockwell products, control logics, SLC 500s with RS Logix 500, and all the way back to a PLC 5, and still have plenty of experience with those systems and can easily add graphics to PLC5 using my favorite graphics package, Factory Talk View. But I also have extensive experience in other graphic packages, GE's Proficiency, Wonderware, PanelMate, PanelView, which is another older Rockwell version. But the point is that I can come up to speed on any form of PLC, any form of graphics package, and either improve an existing control system, design a new system, put it together, and have a very modern and easily operable system. Although my background, as I said, is primarily in power generation, it applies to, which, by the way, from a control system standpoint, it's some of the most complicated and sophisticated control systems, which why I feel confident I can transition into the manufacturing industry and do both regulatory control on an analog process or especially sequential processes on manufacturing lines. So let's get back to the bag house and do the fun stuff. In this example of placing it in service and seeing all the additional features that I using the power of Factory Talk View to provide much more information that's available that wasn't inside the PLC logic, not available on their panel board, but now available through this HMI graphic. In listening to the last scene that I just recorded, I realized that an important part of the aspect of reverse engineering I forgot to mention, I want to cover briefly here before getting into putting the simulation into runtime. When I reverse engineer somebody else's design, in this case, this ladder logic of the baghouse filtration system, one of the most joyous parts of the work that I do, and I love doing, is finding mistakes of the existing system. In this case, with this client, this logic's been operational for approximately 15 years and still to this day is that way. And I found mistakes. When I review this ladder logic and then switch it to and build the Boolean logic, I'm able to review and see the designer's intent. And I found several areas that were causing problems. And that's the beauty of a full simulation where I can build the simulator. I left the original design in there, place the simulator into action, test that area that I saw had some discrepancies, and observe the reaction and go, oh, look at that, it is kept causing a problem. Then go back to the Boolean logic, redesign what I think is corrected, and modify the ladder logic with that correction in there, and then place it back into the simulator and test that in fact it is working correctly. So I was able to, through this reverse engineering, in addition any new design that I do and create, build a bench test simulation and place it in operation and make sure that prior to going back to the site and out in the field, that it's fully functional and tested. So once it's placed in operation and during the commissioning stage, the system works flawlessly, and I've done that many times, or nearly flawlessly, resolving any field issues because the simulation is not actually working devices out in the field. I have logic in here that simulates the field devices, and once you get out in the field, there's oftentimes some timing issues that have to be resolved. So now with that, let's move on to the next section for discussing how the simulator works, the standards and the graphics, and then placing it into operation. To actually run this graphic and interact with the process, in this case, bench test simulation. There's a few standards that I need to go over so that you could see the full potential of this graphic. The very first one that I've encountered out in the industry, it's a difference between the manufacturing industry and the power generation industry. It's the standard regarding the colors green and red. In the power industry, this historically comes from back in the 1940s. Red means hot and green means cold. And so therefore applied to valves like this and motors, a red valve means that it's open, green valve is closed, or on motors, a green motor means it's stopped, and a red motor indication means it's running. The more obvious ones that may not even have to be explained is, in this case, gray is the light is off, and yellow means the light is on. Digging deeper into the functionality of this graphic, it's now appropriate to discuss a very powerful feature of FactoryTalk View, which is called, in their language, touch. So if I move the mouse cursor over various fields, the box will highlight. That means there is a touch function that typically either, in this case, the switch will operate. When I click on it, it'll go from off to manual to auto, then back to manual to off on each click. Or on other areas, it brings up what's called in this language a pop-up, or some people have called it an overlay screen. For instance, if I click on the inlet valve to compartment B, it brings up this overlay screen. And I'll go talk about these overlay screens in a minute. And you can see various pieces of information. And I've designed this graphic so that, to use overlay screens to provide the operator much more information. In addition, what is added to this HMI graphic that is not available on the panel board is a number of indications of status in this area right here that I found when I reverse engineered the logic and created the Boolean logic. It was information that any operator would want to know to see what the logic is doing inside the PLC. When you look at the panel board information, I'll click to that again, for instance, there's not much there except for indicating lights. The annunciator is replicated in the graphic, but what is inside the logic in the PLC has a number of different status things that are not available on this panel board. So for an operator who has available to them the panel board indication, they will be wondering, well, why is the system doing what it's doing? When I reverse engineered the logic that was in there, I discovered a number of different status things that would be good to know, and provided a status panel over here so that the operator can go through and see what's going on. Currently, this initial starting part of the simulation I like is the cleaning is off, the reverse air fan is not running, and the bypass valves are closed so that all the inlet flue gas is going through all 12 of the baghouse filter compartments, and theoretically capturing any particulate matter and sending clean flue gas to the stack. the current differential pressure, which is what is used to trigger a cleaning process. I've simulated 14 inches mercury going in and 10 inches of mercury coming out with a differential pressure of 4 inches. And that becomes important as we place this, because it's the differential pressure that initiates an automatic clean if the cleaning mode is selected there. Now, just to cover the annunciator and then show an example of these overlays versus the status information, the operators on the existing panel, I enjoy going back to that again, they will have these lights that come in. For instance, this picture shows a valve stall alarm is in place, and but the only way they would, in this case, know which valve is not, which valve is basically stuck, is to go and look at their lights, and the logic blinks the lights when it's valve stall. So as long as the light bulbs are functioning, they'd have to go to the panel board and take a look at it. One of the most favorite ones I like is the sequence stall. It will come in and I'll just cover the valve stall in this case. What I did to the graphic to cover this, instead of doing a pop-up to tell them which one, every one of these valves, there's an icon that if the open and closed indications are neither in or both in for a given time period, a yellow S will show up and tell the operator which valve has stalled. If the sequence stall comes in, there is a pop-up that tells them that if either, and the way the nomenclature is set up on this, if either low air supply pressure is active, which in this case is not, or the reverse air fan is not running, which that is the case because the reverse air fan is not running, and bypass valve A, not open limit switch, since it's closed, that one's in. Bypass valve B, not open limit switch, that one's in. And if this was placed in auto, the sequence stall would be there. So in the case of my HMI graphic, what's very powerful is if this alarm comes in, they can click on it and observe why that alarm is in. In the panel board information, the operator doesn't have that capability. If you made it this far in this video production, I'm sure you are probably been patiently waiting to actually see this graphic and fully functional simulator work. So now let's get to it. All right, as I stated in the last scene, all 12 compartments are online, and just to click as an example, the online light is on because the inlet valve is not closed and the outlet valve is not closed. To go to isolate that, the inlet damper has to be not open, the outlet damper not open, which means basically closing these two valves, and the reverse air fan damper, which is this one right here, is not open. And that is true because this one is closed. Those are just, I'll be going through and showing many of these pop-ups, emphasizing the point that when an operator is standing at the panel board, they don't have this ability. They have to use a written procedure and thumb through the pages to find out, well, why is the isolation light not on and why is the online light on, and vice versa. So you're going to see this, and this is a primary benefit of upgrading to an HMI graphic where utilization of the logic can be represented on the screen and available to the operators instead of having to rely on written procedures, memory, and just passing down from one operator to the next who are experts on the system. Okay, here we go. The first step, if you are interested, is how do I get into auto cleaning mode? Well, the light's not lit, so let's click on it. To get into auto cleaning mode, no cleaning in progress, and I think there is a cleaning in progress light. So two different groups of permissives and interlocks. And that reminds me, I need to cover permissives versus interlocks, and these two terms, if you're not familiar with it. Here again, I'm stalling, putting this simulation to do some more explanation, but I feel it's important. A permissive, and this is an example of permissives required for reverse air fan start, mean that these three permissives, which are in the logic in the PLC, have to be okay for the fan to start. But unlike interlocks, once the fan or valve is open, or the permissives have allowed the action to happen, any one of these permissives dropping out will not trip either the valve, motor, or action of the sequence. And interlock, this, for instance, is a interlock. Any one of these will result in a trip open of the bypass valve. Differential pressure greater than 10 inches, inlet temperature below 125 degrees Fahrenheit, or the inlet temperature above 400 degrees Fahrenheit. And in this case, since this is important information, I've even added logic in the simulation that can upgrade the existing PLC to tell the operator which one of these came in first to cause a trip. So interlocks are trips. If an interlock is in place, it will not prevent the item from starting. Permissives are only those items that will prevent a specific action, like a valve opening or a motor starting. So here we go. Now let's place this. Click the switch. It goes into manual. See the switch graphic change, just like you were twisting it. The indicating light telling the operator manual cleaning mode has been selected. Click it again. And now the switch is indicating being in auto, and an auto cleaning mode is selected. Oh, but let's see. The sequence stall, I purposely didn't design into this an audible bell or horn because I find those annoying. I simply used the flashing of the sequence stall light, and it's in, so let's check. Why is the sequence stall in? Well, it's because the reverse air fan is not running, and these other three are true. And this one is because we've gone to auto cleaning mode has been selected. So, and a sequence stall intuitively would mean that the whole cleaning sequence is not going to begin, even if the differential pressure was greater than 5 inches, which is what initiates this, because the sequence has stall. So that's telling the operator, without having to read an operating book, that he has to start the reverse air fan. So as we clicked this before, what are the permissives? This tells them simply just hit the reverse air fan start push button and it'll start. Now, something I want to also mention that I've added here that is not part of the panel board, it's an upgrade and it's using the potential of this, is you may see that on all the valves, there's a box in the top of the valve, and that is a representation of the digital output from the PLC to the solenoid. And in this case, the solenoid, red meaning energized or true, and the solenoid is giving an open command. The body of the valve is used to represent the digital input of either the open and closed digital input switches out in the field. Of course, being a bench test simulation, I have logic in there that represents those field inputs. The panel board only shows lights of the switches. It does not tell the operator that the PLC is energizing or de-energizing the solenoid out in the field to provide an open command. That same is true, I wanted to show this when I do hit the start push button, and the way I do this on motors is the center of the motor will turn red, representing the digital output to energize the motor contactor. The surrounding portion of the motor will be the digital input from the field once the motor has actually started. And here again, I've got additional simulation logic to represent that. So let's get the, oh, by the way, I need to acknowledge this flasher so that it stays in solid. And now start the reverse air fan. You see the red in the center? And then after a time delay, this opens. You see the open command here. The valve is traveling, and when the open switch makes up, the body turns open. Oh, look, and the sequence stall has gone out. So now we're good to go. So the system is ready to start sequencing through an automatic compartment cleaning sequence. And in this case, the logic always starts from in auto and goes from A through L sequentially, one at a time. And so this next scene will be showing a demonstration of that. Now that the baghouse cleaning system is ready to perform its auto clean, I have to show, as part of the simulation, I have a small little pop-up where I can enter the various parameters in there that change to initiate that, and that's just because I don't have a real process connected to this PLC. So I brought this up so that right now we're not in a cleaning sequence because the differential pressure is less than 5 inches. That's what is set in the logic in the PLC. So if I raise the inlet pressure, which is represented here, and enter a value of 16, and the moment I hit the enter key, which you can't see, this will change to 6, and you'll start seeing how with the indicating lights over here on the status symbol, what the PLC is actually doing to understand. In addition, as valves are commanded to change their state, you'll see the respective solenoids change, and then after a time delay, the actual valve change in position. So this will be, it doesn't go too fast, but while it's happening, I'll discuss what's going on. So let me hit the enter key and close my simulation little pop-up so you can see what's going on. Here we go. 16 inches goes in there, close the pop-up. You see 16 inches and immediately cleaning in progress. Light comes down, auto sequence start. Now phase 1, dirty settle, tells you that it's there for 70 seconds, and I've also added the actual timer so the operator can watch the timer increment up to 70 seconds. And dirty settle, by the way, the cleaning light came on. These are the permissives that started. Once it was started, it latched in. The outlet valve goes closed, and what that's doing is allowing the fabric filter bags to collapse. And as they collapse, the ash collected on the outside settles into the bottom of the compartment. When the timer times to 40 seconds, there's going to be 15 seconds of forcing this reverse air fan in here and backflowing through the compartment backwards to get more of the ash to settle. And that goes pretty fast because that's only, as you can see by the light, a 15-second timer. On the panel board, people had handwritten those seconds, but there was no indication of it. So now the reverse air fan, the reverse air valve A has opened and the air is settled out. Now we have clean settle. So that recloses, and for 100 seconds, since that 15 seconds of air burst into the chamber, it's going to create a lot of dust. So for 100 seconds, that dust is allowed to settle because the outlet valve is closed and the reverse air valve is closed. And once that 100-second timer times out, and this takes fairly long. I could have speeded it up by going into the code and changing it, but I like to show the realistic process. But once that times out, we go into the valve travel phase. And if I remember correctly, that is simply allowing the outlet valve to open back up, which allows the flue gas airflow to go back in, and I think the reverse air fan recirc valve opens back up, and then we go into intercycle mode. I can actually click on that to show you what it takes to cause intercycle mode to come in. So we're almost timed out here. Wait a few seconds while this timer gets to 100, and sure enough, both the outlet valve is traveling open and the recirc valve is traveling open because recirc air is no longer needed to do cleaning of this compartment. And we give 20 seconds for those valves to reach their final position. We're almost timed out there. And intercycle mode is active, as you see by the clicking on that, all the interlocks to create that. And that's simply to say, prior to disturbing this flow path and immediately jumping to the next chamber, which is compartment B, I'm going to give it 30 seconds. So now we're cleaning in progress again, and we're repeating. There's the close command to the outlet valve of compartment B. Compartment B is no longer online because the outlet valve is closed. If somebody was wondering, well, why did that light go out? Why did cleaning come on? Oops, looks like I got an issue there. Yep, I'm gonna have to fix that. Well, the cleaning light is on. This went out because the outlet valve was not closed. Cleaning light came on because the cleaning in progress permissive was set, and the timer is going to go through this. Now, I'm not going to continue running this video, except, with the benefit of a simulator is the different things can be done. Like you'd ask the question, what if we have cleaning in progress, which you can click on that. These were all the permissives, and this group here is what caused the auto clean mode to start. And this is sequencing through, and you can watch that. But the simulator allows a person to try different odd events and go, well, what would happen if? That's the benefit of it, to fully test either modifications to the logic or different scenarios. I'm running a typical scenario right now. And here's a very simple one. what if this differential pressure while cleaning drops back within normal? I wondered that myself. And instead of working through, if you only have the ladder logic and you're looking inside the PLC, it's rather rigorous to go through all those ladders to answer that question. Now, the fact that I drew it up in Boolean form makes it easier to see what would happen if the differential pressure drops. Does the cleaning stop or does it continue? Well, with a simulator that was built, and this is why I love doing simulation of existing processes or any of my modifications I've done, or brand new logic that I designed from scratch. I get to run it and test it on the bench before installing it in the field. So let's put the inlet pressure back to 14. Okay. Differential pressure, excuse me, drops to 4 inches. Okay, this compartment is still cleaning. It's still stepping through the steps. Now I wonder, once this compartment is done and after inner cycle mode, will this go to compartment C and continue all the compartments, or will it simply stop? Now the problem, if it stopped, then typically the only compartments that would ever get cleaned is always the first ones up front, obviously. The remaining compartments would never get cleaned. So I'd be interested to make sure, and if I was designing this, that anytime a clean is initiated, all compartments get cleaned that are online. So, oh, look at that. It did move to compartment C. And I won't do it in this video, but I have verified through the simulator that once the differential pressure exceeds 5 inches, all compartments that are online do get cleaned. So let's let this run, and I'm going to return later to wrap up any further explanation. In that last scene that I just recorded, I don't know how many of you have caught a oops, but when I clicked on cleaning to see the interlocks, this area of the graphic didn't have any English descriptions. I didn't notice it when I did it until I went up to the compartment B, clicked on it, and that's when I noticed the same problem was there. This is the beauty of doing a simulation on a bench test system prior to installing the process, the upgrade, is that I can run through all these different scenarios and see where there may be an oversight, a logic problem, something missing in the graphic. And in this case, I had some files that are used to populate the screen that hadn't been loaded on this laptop that I'm doing the work on. So in doing so, I also found that the first half of the compartments, the parameter that populates this field was not in the database on the server, so I also corrected that this morning. And as this goes to compartment B, even though the clean light was coming on, this X wasn't going okay as compartment B is auto-selected, but now that parameter is in there. So here again, this is just a emphasis of why simulation work prior to installation of modified logic, new graphics, modified graphics becomes so important, because it makes the commissioning phase of any project at a facility that much smoother and safer and much more reliable and less time consuming. I was playing around with the simulation in this graphic to speed up getting the sequencer to the compartment L to wrap up this video. So I wanted to show a feature that is used as part of Factory Talk View, and in this that I've included for instructional information to operators. You'll notice that I have isolated compartments C and D. We're wrapping up on finishing compartment B. So this, as soon as this timer goes off, it should go to cleaning of compartment E and jump past these just to speed up going past this. The well, it didn't do it. Now that's interesting. Here again, this is the value of simulating this. This looks like a logic problem inside the PLC from the original design. I'd have to do some research in my Boolean that if the isolation inhibit alarm, and here's the feature, is see this, as soon as I put the cursor over, this pop-up text shows more than 2 comps attempting isolation, that describes why this alarm is in place. Let's see if I can figure out why we're not getting cleaning in progress. Enable cleaning cycle is not lit, so let's look at that light. This is a good exercise in troubleshooting what's going on. I hope my features will enable me to determine this. So we need, for this to be true, to start the next cleaning, we need this permissive enable cleaning cycle, and that's not lit, as can be seen up here on the status screen. Bring that up, and these two counters, not skip compartment, are not true, and not increment compartment counter is not true. Well, unfortunately, I don't have those status indications to research why these aren't true, but it's obvious that if at least 2 compartments side by side are causing an isolation, then the whole cleaning cycle is stopped. And this would be a good opportunity to review this, use the simulation, and do an upgrade potentially where still enable the ability to go isolate these 2 and go to E. As I said, looks like there's an original logic issue here, and some more logic design work would need to be done, then tested on the simulator to allow for this cleaning process to complete. Just playing around with this isolation inhibit feature and letting it sequence it down. It was on, cleaning was being done on compartment F, so I isolated G and not the next one. I left H online, but then isolated I. So when compartment F finished, it skipped over G and did successfully do a cleaning on H. I would expect after H is done, it would skip over I and do a cleaning on J. So through testing, it's obvious that side-by-side compartments, not side-by-side geographically, but side-by-side sequentially, if 2 are isolated, it stops the cleaning process, which for me, that's just kind of cracks me up. But you can isolate every other compartment as long as it's no more than 2, and it will skip over, hopscotch over those and continue to work. Now that's just kind of a weird design. I don't think it should have differentiated between whether they're sequentially side by side versus every other one, but that's just me and my review of this logic. But I thought you'd find that interesting. That here again, simulation and playing with this on the bench discovers potentially logic issues that need to be upgraded. As the sequence nears its completion, currently compartment K is in cleaning mode, and L will be the last one. I want to wrap up this video by offering anybody who is interested in a in-person demonstration. It's nothing like getting your hands on and playing with this to see how it works. To contact me, you can go to my company website, www.laminarenergy.com. At the bottom of the YouTube video page, you'll see how to spell laminar correctly. AR is in the name. Or if this demonstration sparks interest in adding automation to your process or troubleshooting or upgrading, I am very adept at both PLC logic modifications and creation. In addition, as you can see from this HMI graphic example, very adept at creating very user-friendly, intuitive graphics that will assist the operators in operating their process. By the way, this system is not an off-the-shelf purchase, available for off-the-shelf purchase. I would have to be contracted to build a system for you. If you would like, for example, to have a simulation and interactive graphics like this, fully functional graphics like this, specific to your process for upgrading. And the last thing I want to mention, this is a phenomenal operator training tool. Playing around with it, like the example I just showed with why does it do what it's doing when two chambers are isolated side by side versus every other one. So please give me a call or email me. The information is on the website. Thank you very much, and I hope you enjoyed this video.